Hey everyone, welcome back to the Systems Podcast, the show where we break down the systems behind modern software, startups, AI, infrastructure, and engineering at scale.
Whether you're a software engineer, founder, student, or just someone obsessed with how complex systems work, you're in the right place.
Let's get into it.
So, setting the stage for today's deep dive, I think we really need to go back to the early days of big data.
Right, like looking at frameworks like MapReduce and Spark. I mean, they were absolutely revolutionary at the time.
Oh, completely. They solved these massive, previously insurmountable computational problems. We finally figured out how to harness thousands of machines.
Yeah, it's just chewing through petabytes of
Yeah.
information. But, in doing so, we actually created a brand new bottleneck in the engineering pipeline.
Yep, and it wasn't a hardware bottleneck.
Exactly. It wasn't the CPU, it wasn't disk I/O, and it wasn't the network. It was you, the human programmer.
Yeah, I mean, we completely solved the hardware scale problem only to introduce this massive cognitive scale problem.
Right.
Engineers suddenly found themselves spending like significantly more time wrangling different execution environments and writing boilerplate code than actually analyzing data.
Which brings us to the mission for today's deep dive. We are exploring a fascinating 2015 paper from Google researchers about a system called Yettilog.
Yettilog. Yeah.
It's a declarative language built to seamlessly blend data parallel pipelines with raw computation. And the whole goal was to save engineers from what we might call cognitive whiplash.
Cognitive whiplash. I love that. It
Yeah.
captures the day-to-day reality perfectly.
It really does.
To appreciate why a completely new language was even necessary, we have to look at the specific friction points engineers were facing.
Right, when they're trying to query these vast repositories of digital knowledge.
Exactly. We're talking about data sets like crawled web documents, search engine logs, or the massive entity relationship maps in the knowledge graph.
So let's ground this with a really specific example for the listener. Imagine your task is to find a list of influential jazz musicians across a corpus of billions of parsed sentences.
Billions. Yeah.
And you aren't just running a keyword search for the word jazz. You need a structural linguistic relationship.
Right, something highly specific.
Yeah, like you need to find a dependency parse tree showing a grammatical structure like Ellis was influenced by Miles Davis.
And honestly, the sheer mechanical difficulty of executing that request using traditional tools is, well, it's staggering.
It's a nightmare.
Consider the state of the data, right? The text has already been parsed by natural language processing systems. Entities have been resolved to unique identifiers.
Which is great, but
But think of these as universal barcodes for concepts. So the system doesn't confuse the legendary trumpeter Miles Davis with just some random guy named Miles.
right.
Now, the programmer has to comb through billions of these parse trees to find instances where a musician entity is a grammatical dependent of the verb influenced.
Historically, doing this requires stitching together a completely fragmented toolchain.
Oh, absolutely.
First, you have to use a batch pipeline system, maybe like Flume or Hadoop, just to physically iterate over the corpus on disk. So that's language and environment number one.
Yep.
But a batch processor like Flume is incredibly clunky at navigating complex, nested, tree-like data structures.
So for the actual logic of walking the tree, the engineer writes custom imperative Java or C++ code. And that becomes language number 2.
Which you then embed inside the batch pipeline.
Right, exactly. But we still aren't done.
Nope. Once your C++ code extracts the relationships, the output is still massive. You need ad hoc statistical queries to rank the musicians.
So you load the extracted data into a distributed SQL-like system, like Dremel.
Or Spark. And that's language number 3. I mean, I look at this workflow and it reminds me of trying to cook a single complex meal, but you're forced to use a completely different kitchen for every single ingredient.
That's a great way to put it.
You're chopping your vegetables in one building across town, packing them into a cooler, driving to another building just to boil the water.
Just to boil water.
Right. And then commuting to a third building to plate the dish. Rapid experimentation is basically impossible.
The kitchen analogy highlights the core issue perfectly. In software engineering, rapid experimentation is the engine of progress. If you have to commute between 3 different kitchens just to try a new recipe, you're going to stop trying.
Exactly. You just give up.
The fragmentation forces engineers to write massive amounts of serialization code just to pass data from Flume into C++A and out to Dremel. You're constantly translating formats.
So how do we build one single unified kitchen?
Well, this is where Yettilog enters the picture.
Which stands for knowledge logic, by the way.
Right. It marries a classic logic programming language with modern data structures.
Hmm.
Specifically, it's an extension of Datalog.
And for anyone unfamiliar with Datalog, it's a declarative logic language.
Yeah.
There's a fundamental difference between imperative programming, like Java, and declarative programming.
Yeah. In imperative languages, you write step-by-step instructions on how to find the data. Open the file, loop through records, check the condition.
Whereas in declarative logic, you just declare what data you want, and the execution engine figures out the optimal path to get it.
Exactly.
I have to push back here, though. Datalog is famous for flat, highly simplistic logic facts, like textbooks teach it with Socrates is a man and all men are mortal.
Right, the classic examples.
How does a language built for flat facts handle the messy, deeply nested reality of a parsed Wikipedia page without completely breaking down?
That's the crucial question. The engineering team recognized that standard Datalog couldn't handle modern semi-structured data at all. So their core innovation was completely swapping out the native data model.
Oh, interesting.
Yeah, in Yettilog, the fundamental data structure is intrinsically tied to protocol buffers.
Okay, protobufs, which are Google's common representation for serializing structured data.
Exactly. The records in Yettilog correspond directly with protobuf messages. They can have named fields, repeated lists, and they can be deeply recursively nested.
So it maps perfectly to the real-world data.
Yeah. And to interact with these nested protobufs cleanly, the language relies on a mechanism called record unification.
Let's unpack record unification, because it completely redefines how we extract data. It's almost like a visual metaphor, like a cookie cutter.
A cookie cutter, I like that.
Yeah, take that messy Wikipedia document. It's got URLs, timestamps, deeply nested lists of tokens. If you only care about the host name and the parsed tokens, you simply stamp a cookie cutter onto the data set.
Right. In code, you pass a pattern that explicitly asks for hostname, tokens, and then you use this wildcard syntax called .rest.
That REST wildcard is just incredibly powerful.
It really is. It tells the execution engine, match the host name and tokens to my variables and just bundle absolutely everything else I didn't name into this REST pile.
There's no tedious parsing sequence.
Nope. No null checks, no array boundary validations.
Yeah.
The language just unifies your pattern with the underlying protobuf automatically.
And because unification is bidirectional, it works in reverse too, right?
Yeah, you use the exact same cookie cutter syntax to construct brand new protobufs. You declare the shape, and the runtime builds it. It strips away hundreds of lines of boilerplate.
Okay, so we've essentially solved the data extraction and transformation problem. We unified the pipeline.
You did.
But extracting data is rarely the end goal. If our mission is to find the most influential jazz musicians, we don't just need a list of names. We need to do math.
Right, we need to compute statistics, frequencies, graph weights.
Which introduces a massive hurdle for a pure logic language. Traditional Datalog is binary. A fact either exists or it doesn't. True or false.
Exactly.
But when you're counting mentions across billions of documents, you need numerical values. You need states.
And to solve this, Yettilog incorporates what are called weights, a concept inspired by an earlier system called Dyna.
Okay, so how do weights work in this context?
In this paradigm, predicates and logical expressions can have numerical values explicitly attached to them. Think of them as weights on a graph, or just simple frequency counts.
And to manipulate these, the language uses aggregators. We're talking about operators like plus for sums, or min for finding the lowest value.
Right.
So if I want to count how many distinct times Miles Davis influenced someone, I'm not writing a for loop to iterate through an array.
No, absolutely not. You just define a rule with a plus aggregator. The runtime automatically groups the records by their key, the musician's identifier, and computes the combined values.
If I'm an engineer used to writing massive iterative while loops for graph weights, this feels like a total paradigm shift.
Right.
What does it actually look like to just let the language figure out the loops?
It strips away all the structural noise. You're left with pure algorithmic logic. The most stunning demonstration of this is the PageRank algorithm.
Oh, PageRank. That's a notoriously complex dynamic programming algorithm.
Yeah, usually it requires maintaining massive matrices, handling convergence states, writing highly synchronized distributed loops across a cluster.
It's a lot of code.
But in Yettilog, you can write the core PageRank algorithm incrementally in literally 3 lines of declarative code.
Wait, really? 3 lines?
3 lines.
3 lines to replace hundreds of lines of distributed systems code. That is insane. How is that mathematically possible?
The secret is that Yettilog supports aggregations over what mathematicians call semirings.
Semirings. Okay, let's break that down.
It's basically a formal set of rules for how to combine and accumulate values along different paths, like adding up probabilities across a network graph.
Right.
Because the language engine understands the mathematical properties of a semiring, it fundamentally knows the order of operations won't change the final truth. It can take your 3 lines of equations and automatically generate the complex loops needed to solve it.
It just churns until the numbers converge.
Exactly.
You declare the mathematical truth, and the engine handles the mechanical iteration. It's this brilliant fusion of functional and logic programming.
It really is elegant.
However, having elegant 3-line declarative logic is completely useless if it crashes your servers the moment you deploy it against petabytes of data.
Well, theory is great in a vacuum, sure.
Right, execution architecture is what actually matters. How does a single language execute this across a massive cluster without melting the infrastructure?
The transition from an academic language to an industrial strength tool relies on a tri-platform execution model.
Tri-platform, meaning it runs in 3 different environments.
Exactly. The exact same Yettilog script can be compiled to run natively on 3 completely different execution architectures without changing a single line of business logic.
Okay, so platform number 1 is a single machine environment. This is for local testing, rapid iteration on small data sets.
Yep. You don't want to spin up a huge cluster just to verify a parse tree logic works.
Right, that'd be overkill.
Yeah.
Then platform number 2 is the batch platform, built on top of distributed frameworks like Flume.
And this is where it gets cool. When you point your script at a massive corpus on disk, the compiler actually translates your rules into MapReduce jobs.
I love the mechanical elegance of this. In MapReduce, you have a map phase that filters data and a reduce phase that groups it. The Yettilog compiler looks at a logic rule and realizes the if conditions function perfectly as the map phase. And those mathematical aggregators we talked about, they map seamlessly to the reduce phase.
It's a seamless translation. And then you have platform number 3, which is a high fan-in interactive service modeled after Dremel.
Right, for lightning-fast queries.
Yeah, it uses an execution tree. A root node distributes the query to hundreds of intermediate nodes, which query thousands of leaf nodes.
The leaves scan in parallel, pass it back up, and it aggregates on the fly.
Exactly. But compilers aren't omniscient, right?
No, they definitely aren't.
Yeah.
Let's say I'm joining my massive Wikipedia data set against a list of jazz artists from a database like Freebase.
Right.
The compiler might assume both data sets are massive and attempt a distributed shuffle join.
Which is painful. A shuffle join requires moving terabytes of data across the network so matching keys end up on the exact same machine.
It's intensely slow and expensive. But as the programmer, I have domain knowledge. I know there are only a few thousand notable jazz artists. That list easily fits into the RAM of a single machine.
And the engineering team anticipated this exact problem. They knew they couldn't pretend their query planner was perfectly intelligent, so they introduced physical annotations.
Physical annotations, how do those work?
Instead of letting the compiler guess, the programmer adds a simple at small annotation next to the jazz artist predicate.
Oh.
It tells the planner, this dataset fits in memory. Do not initiate a network shuffle. Just broadcast this small table to the RAM of every single worker node.
You can also use @mode annotations to dictate the direction of a join, right?
Exactly.
It functions exactly like giving a GPS app a gentle nudge.
Oh, the GPS analogy is perfect.
But the app understands the general route, but you as the local driver know there's heavy construction on Main Street today.
Right.
So you just drop a pin to force a detour. You don't rebuild the engine or take over the steering wheel. You just guide the system.
It offers physical transparency while maintaining the high-level logic.
So we have protobuf native structures, automatic loop generation, GPS-style compiler hints. Does this hybrid actually survive contact with production reality?
It does. Internal teams utilized it for a wide variety of tasks. Everything from ad hoc NLP analysis to building massive data integration pipelines.
But the use case that stands out the most is the live production pipeline for classifying malware.
Oh, yeah. The security domain relies heavily on evaluating massive arrays of signals.
Right, and the input signals describing a potentially malicious web page arrive continuously as protocol buffers.
So engineers wrote Yettilog rules to match specific combinations of these signals, compute a risk score using aggregators, and classify new malware live as it flowed through.
That's intense. Live production is the ultimate crucible for a new language.
Definitely. And the performance was more than sufficient. But the most impressive outcome was the drastic reduction in code complexity.
You're talking about the C++ rewrite, right?
Yes. There was a specific case study where an expert programmer was tasked with rewriting an existing, highly optimized C++ pipeline using Yettilog.
C++ versus declarative logic. Who wins?
The rewrite was completed in just a few days, and the resulting Yettilog program required 70% less code than the original imperative C++ implementation.
Wait, 70%? That is massive. The reduction in maintenance burden alone makes that a monumental win.
It does, and to take that a step further, because the code was so concise, just pure algorithmic logic, it actually exposed serious logic bugs that had been hiding inside the original C++ code for years.
Oh, wow. So the boilerplate was actually masking bugs.
Yeah, the legacy code had subtle errors in handling subset matches. Imperative code forces engineers to interleave business logic with memory management, null checks, buffer sizing.
Right. Over the years, complex heuristics just get added as workarounds for legacy infrastructure limitations. They become fossilized workarounds.
Exactly. When Yettilog stripped all of those fossilized workarounds away, the actual logical errors were suddenly completely visible.
Raising the abstraction level provides profound clarity. When you don't have to manually manage memory, you clearly see what your program is fundamentally trying to achieve.
Yeah, you really do.
But there is one final architectural feature we need to explore that highlights just how modern this runtime is.
RPC integration.
Yes. In a modern data center, you're constantly communicating with live microservices. You have to handle remote procedure calls.
And integrating an external API into a high-throughput pipeline is usually an absolute nightmare of asynchronous callbacks, thread pooling, error handling.
It's messy. How does Yettilog handle it?
It circumvents the mess by treating RPCs simply as standard predicates.
Okay, so if I want to run parsed English documents through Google Translate, I don't write a complex REST client.
Nope. You simply invoke a predicate named to French, pass in your English text variable, and it evaluates to the French translation. Syntactically, it looks identical to querying a local fact.
I understand the syntactic appeal, but mechanically, how do you avoid the latency trap?
Latency is the big question.
Right. If every single sentence evaluation triggers an individual network call, the latency would be catastrophic. Even a 10-millisecond round trip spread across a billion sentences would take lifetimes.
Treating a network call identically to a local lookup definitely invites latency disasters if not managed at the compiler level.
So how does the runtime hide it?
Through a highly sophisticated automatic batching mechanism. Under the hood, when the engine evaluates a rule and hits that network call, it doesn't block the thread.
Doesn't wait.
It does not wait. It suspends that specific logical evaluation, parks its state in memory, and immediately moves on to process the next record.
Oh, wow.
Yeah. Once it collects a large enough batch of these suspended requests, it fires them off in one massive optimized network call.
And when the results come back?
The engine automatically wakes those specific evaluations back up and resumes the pipeline.
That is brilliant. The runtime absorbs the distributed system's complexity entirely. It lets the pipeline maintain massive throughput without forcing you to write a single line of custom batching logic.
You're making the system work for you instead of constantly working around the limitations of the system.
It represents a distinct vision of programming where the runtime handles the mechanical execution, leaving the human engineer completely free to focus on domain logic.
It really is a beautiful vision.
And that vision leaves us with a compelling question to consider as we wrap up. If a language developed over a decade ago could so elegantly blend data parallelism, external microservices, and pure math while eliminating 70% of the code base.
Why do we still widely accept the fragmented, boilerplate-heavy data stacks we use today?
Exactly. We're still routinely jumping between batch processors, imperative glue code, and SQL equivalents.
Yeah, we're still commuting between kitchens.
Right. What if the next massive leap in AI and data science isn't just about throwing more compute at bigger models? What if the real unlock is adopting declarative languages that completely remove the friction of feeding those models knowledge?
We might not need better ingredients. We might just need a unified kitchen.
That wraps up today's episode of the Systems Podcast.
If you enjoyed this episode, make sure to follow the podcast, leave a rating, and share it with another engineer or tech enthusiast.
And remember, great products are built on great systems.
We'll see you in the next one.